I always wanted to own a telescope. Just the thought of being able to see the celestial objects I've seen on TV or read about in books with my own eyes fascinated me. Since I started this YouTube channel, I'd been saving up to eventually buy one. But good telescopes are not affordable by any means. For the budget I had, I could only get cheap refractor telescopes with about a 50 mm aperture. With such a small aperture, the views quickly become dim and blurry at higher magnifications. You can see the moon and a few bright planets, but not with much detail. So after spending almost a year looking for decent affordable ones, I finally decided the best telescope for this budget would be to make it myself. With a massive 114 mm aperture, it could gather over 5 times as much light as a 50 mm telescope and probably provide enough detail to view Jupiter's cloud bands and Saturn's rings, all for just 8,500 rupees or about $90. In this video, I'm going to show you exactly how I built Astra, a super smart digital telescope from scratch. Part of this project is sponsored by Justway, more on them later. I started by researching existing open source telescopes that others had already built. There's no point in reinventing the wheel. The most popular ones I came across were the Hartley telescope and the PiCon telescope project. The thing that attracted me to the PiCon was its use of a cheap PVC pipe for the main body and a Raspberry Pi camera mounted directly at the focal plane instead of using an eyepiece. The only downside I could see was the fairly expensive Raspberry Pi and the fact that you had to connect it physically to a PC and a power cable to view the image. But those were problems I could easily solve. Before starting any project, understanding how it works makes everything easier later on. A reflecting telescope uses a concave mirror to collect incoming light and focus it to a tiny image. Then a secondary mirror and eyepiece is used to make the image viewable. Two things mainly determine how capable a telescope is. The first is the aperture, the diameter of the primary mirror. A larger aperture collects more light, making faint objects brighter and revealing finer details. The second is the focal length, the distance between the mirror and where it focuses all the incoming light. A longer focal length produces a larger image at the focal plane. Instead of using a secondary mirror and an eyepiece, we are placing a Raspberry Pi camera directly at the focal plane. The camera sensor simply captures the image that the telescope forms. There's just one problem. The camera already has its own lens that's designed to focus light onto the sensor, but our telescope has already done that job. So we remove the camera lens entirely, exposing only the image sensor. Then all we have to do is position that sensor exactly at the telescope's focal point. For this design, we want a 114 mm diameter and a 700 to 900 mm focal length mirror. Finding reliable sellers online isn't easy. I spent weeks researching and eventually found a few reliable sellers. I've attached links to both Indian and international suppliers in the description. After the mirror arrived, I gave it a quick visual inspection to rule out any major scratches, chips, or coating damage. And whatever you do not touch the reflective surface. Even if there is a little dust on it, it's usually better to leave it alone or gently blow it off. Improper cleaning is far more likely to damage the mirror than a few specks of dust. I then downloaded the official PiCon STL files from Thingiverse. I was about to send them for printing when I suddenly realized, what if they didn't fit my PVC pipe? So I first purchased a standard 5-inch PVC pipe. Make sure the length of the tube is at least as long as the focal length of your primary mirror. Mine had a focal length of 700 mm, so I cut the tube to 750 mm just to be safe. Then I measured the tube's actual inner diameter and realized it was 5.25 inches, not 5 inches. So I modified the designs to match my tube. While I was at it, I made a few design upgrades too. I used a remix of the camera mount that included a 3D printed rack and pinion focuser. I also redesigned the Raspberry Pi mount to hold my electronics. Plus, I designed a simpler universal tripod mount and a smartphone mount for a neat smart feature I'll talk about later in the video. If you want to use my 3D files, the link is in the description. I also included a link to the original PyCon files. Just make sure you measure your PVC tube first and use the version that matches its diameter. Once all the designs were ready, I sent them off for 3D printing. I recommend using PETG or ABS instead of PLA because they're much more resistant to heat. Telescopes rely on precise alignment, and if the printed parts warp in the heat, it can throw the optics out of alignment. Now there are two more concepts we'll need to understand before we start assembling: focus and collimation. Let's start with focus. The primary mirror forms an image at a specific distance. By moving the camera sensor slightly forward or backward, we can place it exactly where the image forms. This is called focusing. The second concept is collimation. All the light from the mirror needs to be pointing in exactly the right direction so that every bit of light ends up at the same point. If they are even slightly misaligned, the image becomes softer and loses detail, even if the telescope is perfectly focused. This alignment of the mirror is called collimation. Once the printed parts arrived, I gave them a quick visual inspection. There are two main optical assemblies. The first is the primary mirror cell. This consists of a mirror mount, which the primary mirror will later be attached to, and a mirror base, to which the mount will be connected. This assembly helps with mirror collimation using 3 M8 nuts and bolts. Pass each bolt through the holes in both the base and the mount. Then insert the hex nuts into the hexagonal cutouts on the mount. Make sure to place a 10 mm diameter compression spring over each of the 3 bolts. These springs keep constant tension on the mirror mount so the mirror can stay securely locked in its adjusted position after collimation. The second optical assembly is the camera focusing system. This consists of a spider assembly to which I've already attached the pinion using a long M5 threaded bolt. The camera mount has a matching rack that slides smoothly through the center cutout in the spider and meshes with the pinion. Turning the long bolt should now move the camera mount smoothly back and forth. Now let's move on to the PVC tube. I lined the inside of the tube with matte black chart paper to reduce internal reflections. The outside was spray painted white for aesthetics. Next comes one of the two most delicate parts of this build. But before we move forward, a quick word from our sponsor, Justway. For sensitive projects like this, where good quality 3D printing really matters, using a reliable manufacturing service can make a big difference to the final result. That's where Justway comes in. Besides 3D printing, Justway also offers CNC machining, sheet metal fabrication, injection molding, and other manufacturing services. So whether you are building a one-off prototype or something larger, they've got you covered. They support a wide range of materials and provide instant online quotes, making it easy to compare different options before placing an order. Their website is also super easy to use. Simply choose the 3D printing service, upload your STL files, select the quantity and material, and then choose a color if it's available for your selected material. Once you've selected your options, enter your email and submit the request to receive an instant quote. If you're working on your own engineering projects, definitely check them out. Thanks again for Justway for sponsoring the video. Now let's get back to building the telescope. For receiving the image, we are using a 5 megapixel Raspberry Pi camera module. Like I mentioned earlier, the lens needs to be removed to expose the bare sensor. First, we need to unplug the camera from the circuit board. Then we can carefully use some pliers to twist and unscrew the lens module. The module is attached with a bit of glue, so it might take some effort initially. After removing the lens, don't throw it away. You can place it on your smartphone camera for some amazing micro photography. Now we can assemble the spider module. I first screwed the spider to one end of the PVC tube with self-tapping screws. I also screwed the electronics holder plate while I was at it. Then we can use tiny M2 nuts and bolts to mount the camera module to the camera mount. Now we use double-sided foam tape and carefully stick the mirror on the mirror mount. Before screwing in the tripod mount, we need to know the center of gravity of the whole assembly. So we first screw in the mirror assembly and then place the whole thing on a fulcrum and mark the center of gravity. Remove the mirror assembly and screw the tripod mount and the smartphone holder on the CG line. I also added a nice focus wheel to the spider. With that, we have completed assembling the telescope hardware. Next, let's move on to the electronics and software. Instead of using a Raspberry Pi 4, we are using a Raspberry Pi Zero 2W. It's much cheaper, more compact, and has built-in Wi-Fi, which you'll soon see is a really useful feature. One thing to note is that the Pi Zero uses a different camera connector, so you'll need the correct camera ribbon cable. The standard Raspberry Pi camera cable won't fit. Let's start by installing the software. First, download Raspberry Pi Imager from the official Raspberry Pi website. Then insert a micro SD card. I recommend at least 4 GB. Since storage prices have gotten pretty outrageous lately, I'm actually using a recycled flash drive with a USB adapter. Rather than making the video even longer, I've put together a detailed step-by-step PDF guide that covers the entire software setup. You'll find the link in the description. Once your Pi is configured, we are ready for the final assembly. To power the Raspberry Pi, I'm using a single 18650 lithium-ion battery along with a 5V 2A boost converter. This makes the entire telescope completely portable with no external power cables required. The wiring is pretty straightforward, and I've linked a detailed guide and circuit diagram in the description. I mounted all the electronics to the electronics holder plate using double-sided tape. Next, slide the camera mount into the spider assembly and connect the camera ribbon cable to the Raspberry Pi. Only after everything else is installed do we install the primary mirror. This greatly reduces the risk of accidentally scratching or damaging it during assembly. Finally, I added a protective cover for the electronics along with some graphics and QR code on the side of the telescope. That QR code will come in handy very soon. And with that, the build is complete. Now it's finally time to use the telescope. Attach the tripod mount to any standard photographic tripod. Depending on the weight of your telescope and the stiffness of your tripod, it may be a little wobbly, so I definitely recommend using a sturdy tripod if you have one. Now power on the Raspberry Pi and wait for about a minute. You should see a new Wi-Fi network named Astra. Connect your phone to it, then open astra.local. I added a QR code to the side of the telescope so I can open it instantly. A web interface should appear with a live camera feed and a few controls. The exposure and gain sliders are there for more advanced users, but I've already created presets for the moon, planets, and deep sky objects that should work well in most situations. Whenever you want to save an image, just tap the capture button and it will download straight to your phone. Now we need to point the telescope at something. Download an astronomy app like SkyMap or Sky. I've linked a few reliable ones in the description. Allow location access, then attach your phone to the phone mount. Search for the object you want to observe. I highly recommend starting with the moon since it's the easiest target. The app will guide you until the telescope is pointing in the right direction. At this point, you'll probably see a black screen or a blurry white blob. That's completely normal. This is where the focus knob comes in. Slowly rotate it back and forth until the image becomes sharp. If you still can't get a crisp image, you may need to make some small collimation adjustments using the 3 bolts on the mirror cell. But if you mounted the mirror flat and close to the center, you probably won't need to adjust it much. Unfortunately, because it's currently monsoon season here in Bangalore, I couldn't capture any planets. But one night the moon finally showed up clearly, so I quickly took the telescope out into my balcony. My tripod is a little shaky, but once everything settled down, I managed to capture some nice shots of the moon and its craters. I did have to increase the exposure and gain a little. The images aren't the sharpest, but considering they were taken from the middle of a city through humidity and light pollution, I'm honestly very happy with the results. So, was it worth it? Absolutely. Not only is it incredibly difficult to find a commercial telescope at this price that offers similar capabilities, but building it taught me a lot about optics, astronomy, and telescope design than simply buying one ever could. Now all that's left is to wait for the monsoon skies to clear. As soon as I capture an image of the Jupiter, Saturn, or maybe even a few deep sky objects, I'll probably upload them as a YouTube short. Until then, I hope you have fun building this telescope. Thanks for watching. Thanks again for Justwave for sponsoring the video.